Okay, so we're going to talk about dipoles, and dipoles sounds like a strange term, but it just refers to the distribution of electrons when we have a bond. So in the case of carbon monoxide, we have a triple bond, but those 6 electrons are not being shared equally, and we know that because of the differences in electronegatividity of carbon and oxygen. So don't recopy the electronegativities table you see there. You already have that in your notes. Just flip back to it if you want to, or just look at the one that I have here. Carbon has an electronegativity of 2.5, and oxygen is 3.5. So quite a bit stronger pull on those 6 shared electrons that oxygen has compared to carbon. So what we're going to do is actually draw a little arrow, and it doesn't matter whether you draw it above or below the bonds, but it should be drawn parallel to the bonds. But it's an arrow that describes which direction the electrons are being pulled, and they're being pulled towards oxygen. And then we also put a little slash through the tail of the arrow. And what that reminds you of is that end, the carbon end in this case, is the more positive end of the bond. And it would be more positive because the electrons are negative and they're shifting in the other direction. So what we've just drawn is a dipole. So it's describing the distribution of electrons along a bond. Another one, for example, if we were to do a water molecule, we have H2O, and we have these 2 bonds. We can draw a dipole along both bonds. Hydrogen is 2.1. Oxygen is 3.5 once again. So once again, oxygen wins out and is going to pull those electrons toward it. And so I'm going to draw dipoles, again, parallel to the bonds. And I'm going to draw a dipole every place I have a bond. Okay? So I have 2 dipoles in that particular molecule. Okay. So what happens when we have molecules that have multiple polar bonds? And by polar bond, what I simply mean is, if I go back up here, this is a polar bond, and so is this one over here. And that simply means that the electrons are not evenly distributed throughout that bond. A nonpolar bond would be like 2 oxygens bonded together. Because those 2 oxygens have the same electronegativity, the electrons would be evenly distributed throughout that space between the 2 oxygen atoms. So that would be a nonpolar bond. But if we do have multiple polar bonds within a molecule, they can either add up or they can cancel. So an example of them adding up would be like in the case of water. So H2O, we have 2 dipoles. Now, they're not both heading in the exact same direction, but they're not also heading in exact opposite directions. But they're both kind of going, from the hydrogen end towards the oxygen end of the molecule. So I would say that this is a polar molecule because they're adding up. Another way of looking at it is, if I put the first dipole down, I sort of like bring it, from over here to over here, and then at the tip of the first arrow, I put the tail of the next arrow, just like this. Let me try that again. So kind of more like that. And then if I add them up, the overall result, going from the tail of the first arrow to the tip of the second arrow, is a dipole in that direction. And so that becomes my molecular dipole. And anytime there's a molecular dipole, we say we have a polar molecule. They can also cancel out and become a nonpolar molecule. A prime example of that would be carbon dioxide. So carbon dioxide is just CO2. And once again, if I look up my electronegativities, carbon is 2.5, oxygen is 3.5. So we're going to end up, switch over to red or something here. So we're going to end up with dipoles heading out towards oxygen. Well, you got one that's going east and one that's going west. They're pulling in opposite directions, and so those two opposing forces are going to cancel each other out. So this would be considered a non-polar molecule. Okay, so water's polar because its dipoles add up. Carbon dioxide is non-polar because its cancel out. So let's try a couple. To see if you can figure out a couple on your own. Okay, so I've drawn NH3 and I've drawn SO3. So take a look at your electronegativities. Draw the individual dipoles if they exist. In other words, if there's an electronegativity difference between these two. And then see if you can come up with the net molecular dipole, or in other words, the overall dipole. And if there isn't one, you just simply say non-polar molecule like I did for CO2. Let's go ahead and pause the video and give those a try. And then when you unpause it, we'll see the answers. Okay, there you have your answers. N is more electronegative than H, so all of your dipoles are going in towards N, nitrogen, and then your overall or molecular dipole would be going up because these two dipoles at the top are heading in opposite directions, and just like with CO2 where they're pulling out in opposite directions, when they're heading in opposite directions they're going to cancel each other. And then with the SO3 it's a little bit trickier to see, but we have all of them canceling, and that's because we have an up, we have a down and to the left, and we have a down and to the right, which means we're kind of, it's kind of like a three-way tug of war where they're all canceling each other, pulling in opposite directions. So that's a non-polar molecule. And then the last thing we want to be able to say is, well, what if a molecule is polar? If it's polar, that means it has a positive end and a negative end. So for example, NH3 has a more positive region, which would be the hydrogen region, and a more negative region, which would be the nitrogen region, because that's where all the electrons are being pulled. And if it's polar, that means that molecules are going to attract each other more. That's going to lead to something called intermolecular force, or van der Waals forces, and we're going to talk about those in class next time. Non-polar molecules that don't have those are going to tend to attract each other less, and that's going to lead to things like lower boiling points and faster rate of evaporation, things like that. And we'll talk more about those in class next time.